a 744 billion parameter AI reportedly executed with only 25 gigabytes of RAM, while its full precision weights were described around 1.5 terabytes. The model did not fit inside that memory. Colibrì executed it while most routed expert weights remained on NVMe storage. Colibrì is the proof of concept attributed to Vincenzo, also known as JustVug, built around the sparse GLM 5.2 model. The target is GLM 5.2, reported as a 744 billion parameter mixture of experts model with about 40 billion active per token. The original low memory setup reportedly generated only 0.05 to 0.1 token per second, nowhere near practical conversation. At that reported cold rate, one token takes 10 to 20 seconds, and 100 output tokens take roughly 17 to 33 minutes. So the breakthrough is not miniature weights or instant speed. It is turning inference into dynamic placement across storage, memory, and compute. A mixture of experts model uses a router to select a small subset of specialized blocks for each token instead of evaluating every expert. Parameter count describes total model capacity, but sparse execution means only about 40 billion parameters are active for a token. The choice is made per token, not once per question, so successive tokens can demand different expert combinations. Attention, embeddings, shared experts, and other always used weights stay resident because every token needs stable access to that dense core. Verified breakdowns place that resident dense section near 9.9 gigabytes at int4, consuming a large share of the headline memory budget. Meanwhile, the routed experts occupy roughly 370 gigabytes in the int4 container, far beyond the available RAM in the demonstration. The reported layout contains 21,504 routed expert blocks distributed across the MoE layers and the multi-token prediction head. Each routed expert block is reported around 19 megabytes at int4, making every cache miss a substantial storage delivery. For each token, GLM 5.2 reportedly selects 8 routed experts in every MoE layer, multiplying the storage work across the network. That selection repeats across 75 MoE layers, so a single generated token can trigger hundreds of expert accesses. Multiply those reported layers, selections, and block sizes, and a cold token can require about 11.4 gigabytes of expert reads. On the developer's roughly 1 gigabyte per second storage path, disk alone needs about 11 seconds for that cold token payload. That storage calculation implies a ceiling near 0.09 token per second before CPU overhead, matching the observed 0.05 to 0.1 range. Colibrì treats NVMe, system RAM, and optional accelerator memory as tiers of one active hierarchy rather than separate hardware islands. When the router selects an expert, Colibrì checks RAM or optional VRAM first. Only a miss triggers an NVMe read. A per-layer least recently used cache keeps recently needed experts in memory, hoping future tokens request them again before eviction. The design also uses a learned pinned hot store and the operating system page cache to preserve repeatedly useful expert data. Colibrì reportedly prefetches and pipelines cold expert reads while resident experts compute, trying to overlap storage latency with useful work. With little free RAM, selected experts are frequently absent, forcing the SSD to serve the same kind of expensive delivery repeatedly. When an expert is already cached, storage disappears from that access, and CPU matrix multiplication plus memory bandwidth become the next constraints. At 24 to 32 gigabytes, dense weights, KV state, scratch buffers, and operating system headroom leave only a tiny expert cache. One reported 24 gigabyte test reached only a 3 to 4% expert hit rate and 0.07 token per second despite strong direct reads. With more RAM, frequently activated experts can remain pinned, so stable, repeated workloads may benefit more than unrelated one-off prompts. A cache learned from coding tasks may help less when the workload suddenly becomes legal research, because expert popularity can change. Consumer SSD boxes advertise sequential speed, but Colibrì performs parallel reads of roughly 19 megabyte blocks scattered across a 370 gigabyte model. In one same machine comparison, measured disk bandwidth rose 5.8 times, while generation improved only 2.9 times, from 0.10 to 0.28 token per second. Once storage improves enough, the limiting stage can shift into quantized matrix multiplication, CPU resources, or system memory bandwidth. Cache hits remove disk reads, but they do not remove the work of multiplying expert weights or moving those weights through memory. Early coverage reported no GPU support yet, while a later verified review described experimental CUDA and metal execution paths. Optional accelerator memory can hold hot experts, but any missing block still travels from NVMe through host memory before acceleration helps. One clean RTX 5090 rerun reportedly showed roughly zero gain because storage remained limiting and that CPU already matched expert matrix multiplication. A later review reported 1.23 tokens per second on a tuned 121 gigabyte system with Gen 5 NVMe and an RTX 5090 hot tier. 6 RTX 5090s with 251 GeB of host memory reached a reported 6 tokens per second. But that is no longer ordinary consumer hardware. GLM 5.2 includes a multi-token prediction head that can draft multiple tokens for verification, potentially reducing expensive serial decoding steps. With the correct int8 MTP files, the project reported 39 to 59% draft acceptance and 2.2 to 2.8 tokens per forward pass. A common pre-converted mirror reportedly shipped int4 MTP heads that produced almost no accepted drafts, silently disabling the useful path. On a cold cache, verifying more draft tokens can route extra experts. Reported expert loads rose from roughly 660 to 1,100 per token. A reported router option reduced disk traffic and improved one 24 gigabyte run from 0.07 to 0.11 token per second. Restricting router choices may reduce traffic, but the verified review warns builders to benchmark quality again after changing expert access. The roughly 11 gigabyte cold token figure describes reads, not writes, and Colibrì's expert streaming is reported as read-only during normal inference. If RAM runs out and the operating system swaps active buffers, writes surge while performance collapses, creating the worst possible combination. Even read-heavy inference can heat an SSD under sustained transfers, and thermal throttling can quietly reduce the bandwidth the runtime depends upon. The int4 checkpoint is roughly 370 gigabytes. The verified review calls a dedicated 1 terabyte NVMe a comfortable recommendation, not a code requirement. Colibrì's compressed conversation state is reported around 182 kilobytes per token, adding memory pressure as the active context grows. At 1 million tokens, that state alone would be roughly 182 gigabytes before weights, scratch space, or the expert cache. Colibrì proves oversized sparse models can execute locally, but the verified sources do not describe the 25 gigabyte setup as normal fast serving. A later review says its OpenAI-compatible API is not equivalent to production VLLM or SGLang infrastructure with mature serving evidence. The strongest present use is feasibility research, testing private prompts, studying expert activation, and identifying which hardware tier actually limits a workload. Occasional offline evaluation may tolerate long waits. Interactive coding, customer-facing requests, and sequential agent calls compound the reported latency painfully. The verified review recommends building 30 to 100 representative prompts with an acceptance rubric before sizing hardware around public headline results. Record exact RAM, storage path, CPU, accelerator tier, cache state, runtime version, context, and output length before comparing token rates. Developers Digest argues cloud access or conventional quantized deployment remains more practical for production and ordinary coding than this speed-first sacrifice. Developers Digest describes active development, performance work, community contributions, and planned open code integration for fully local agentic workflows at reduced speed. Colibrì belongs to a broader shift from loading everything into GPU memory toward dynamically placing active weights across a hardware hierarchy. The verified essay connects Colibrì with MoE Infinity, Fiddler, FlexGen, LLM in a Flash, PowerInfer, and Air LLM as related placement approaches. Dense models benefit much less because nearly every parameter is needed per token. Independently stored experts make sparse Molovsky models the natural target. Colibrì did not make 744 billion parameters fit in 25 gigabytes or run fast. It made model placement a software decision,